Hello, welcome back. So today we're going to work on application 8, which is the dynamic bolt problem. We're actually going to take the assembly we modeled last time and drop it. We're going to use a couple of interesting features here from the practical point of view in finite elements. And those are primarily covered here. The first one is discrete and rigid bodies. So we're going to drop this assembly onto a rigid floor. Okay, so we're going to learn how to create rigid bodies, very useful. And then we're going to also look at reference points, which are actually used in rigid bodies to define them. And then finally, to pass our simulations off from last week's application to this week's application, we're going to make use of restart files. So we actually have to create those, and I'll walk you through that. So let's talk a little bit about some of the concepts here. Discrete or rigid bodies. A rigid body is associated with a point called a rigid body or reference point whose motion governs the entire rigid body. So in our case, what we're going to do, we're going to have something like this, and you have this planar rigid body that we're going to define. That's going to be attached to what we call a reference point. And we're going to apply boundary conditions on the reference point, and the whole entire part will move according to what we apply at the reference point. They can be used to prescribe the motion of a rigid surface for contact modeling. It can consist of nodes, elements, surfaces, and act as a method of constraint. And it's really nice because it doesn't affect the efficiency. Because it's rigid, we're not having any displacements, which means we don't have to solve for displacements. So it's very easy to model. Basically, what happens in a rigid body is that the relative positions of the nodes and the elements that are a part of the rigid body remain constant. Okay, so there's zero displacement. I shouldn't say that. You actually don't have, you can have displacements of a node, but there's no strain developed. And I guess a way to say it, there's no deformation of the part. And so you can have a translation, you can have a rotation, so there is displacement, but there's no displacement with respect to each of the nodes, if that makes sense. Elements are not able to deform, but they can undergo large rigid body motions. Rigid bodies can be used to model very stiff components, obviously, either fixed or undergoing large motions. For example, things like punch, die, draw bead, roller are great cases. So imagine you want to study the plasticity, for example, of a part being rolled or a metal being rolled. You might not care about the deformations in this hardened roller, right? You might have they're very small, and so you might not care about them. So why not just model it as a rigid? That's a good example of when you'd use this. They can also be used to model constraints between deformable components, and they're a convenient method to specify certain contact interactions. They're also can be used with connector elements such as springs or dashpots to model a wide variety of multi-body dynamic problems. One of the most useful cases is when you have a very large assembly of multiple parts and you want to sort of debug or get your simulation going, right? So instead of putting everything as deformable right away, which can cause a lot of complexity, what you might want to do is only have one component as deformable and leave everything else as rigid. And so you can slowly add in components being deformable, and so you can help debug your problem, your finite element model. So again, the principal advantage to representing portions of the model with rigid bodies rather than deformable elements is computational efficiency. It's very fast because you're not solving for deformations or displacements with respect to each other within the part. One of the things we use to define the rigid body is a reference point. And it's a point that you can create in Abacus, kind of in the same style of we did partitions and datum points and datum planes, datum axes last time. So it's kind of a similar thing as that. It can be attached to a native geometry. So we're going to attach it to some vertices in this case, in this application, but you can also do a piece of the mesh, so a node, and you actually don't even need, it can be any spot in space if you want to define it like that. You can do that as well. So they're used a lot for circular objects. So let's say you have something rotating. How do you put those boundary conditions on? Well, you define a reference point at the center of that circle or cylinder, and then you would apply a rotation to that rotational condition to the reference point, and then tie a surface to that reference point. So that's a common way to do that. The other thing we're going to use in this application is restart files. They are given the .res extension when we create them, and we use these to continue analysis from a specified step of a previous analysis. So by default, no information is written, so we're actually going to have to rerun last week's simulation to get that restart file. And it can also be used, we're going to use it to create initial conditions to our model from one step type to the next. That is, in our case, we had a static step, and now we're going to be doing it explicitly. And then the other thing it's used for is when you have like a dynamic simulation that is maybe going unstable. So it can save, you can create the frequency such that it writes out like every 100 steps or something. And so you have a spot where it'll pick up from if your simulation crashes. Okay, it's another useful use of restart files. So there are some things you have to be aware of and careful of when you use restart files. So for example, the two files you use and what you restart from has to be consistent with what you're trying to send it to restart to. So that's probably kind of confusing, but you want to have consistency between your restart file and what you're actually running, your model you're trying to run from. So we're going to walk through that and pay attention to that. Like for example, we're going to check the element types in this case. All right, with that, let's go ahead over to ACI and get started on this application. Okay, I'm over on ACI. You can see that I've actually made a directory, app8, so that's in my work, classes, ME461, and app8. I'm going to go ahead and load up Abacus, and then I'll launch it using VGL run Abacus CAE space ampersand. All right. And once that opens up, we can go ahead and open up our previous application from app7. So this is that file here. Remember, we had 3 different parts here. The first thing I'll do is go ahead and save as, I'm going to create it just so in case I overwrite it or something like that. I'm going to save it into the app8 directory and rename it app8. Say OK. And so there we go. The first thing I'm going to do is create a part. And for this, it's going to be a 3D discrete rigid. Okay, so we're going to define the type as discrete rigid. And this is going to be a planar shell. So we're going to do a planar. So we have a 3D part, discrete rigid, and a shell. Say continue. We're then going to create that geometry. So create a rectangle, and we'll key it in as 0, 0, and 0.04, 0.04. Say done. Okay, so there is our part. We can then go to the assembly module and create an instance for that. So in order to do that, we click on this button here. Now, you can see actually that it's cutting the current assembly that I had. Okay, so in any case, what you just do is select part 4 and say OK. So yeah, there we can see it's cutting that, but that's okay. We'll take care of that. What you want to do is go over to the assembly tree here and drop down the instances and make sure that you don't have like, for example, 7. So when you clicked on this, if you were to select all of these, you would have got double instances, which you don't want. Okay, that's why I only clicked on part 4 and said OK. So you should only have 4 instances listed there. Now we want to move this part so it's aligned correctly. Okay, so we're going to select this option here, which is translate the instance. And then it says select the instance to translate. We'll select this, say done. And then it says select a start point for the translation vector. So we'll just define this as 0. and then it says select the endpoint. And so based on that start point of 0, 0, 0, where do I want to translate? How much do I want to translate in the X, Y, and Z for that component? Now I've already figured out what we need to put there, so we're going to put negative 0.018, negative 0.012, and 0.0336. Enter, and there we moved it, and we get a message down here, position of instance OK. Say yes. All right, so now if I align this in certain ways, okay, and I can turn off the perspective off, and if I zoom in on that interface, okay, what you see is I actually positioned it so there's a little bit of space in between the bolt and the planar face. And the reason is that we are going to apply, we want contact to be able to be used here. So we want to give the contact algorithm a little bit of space where it can try to pick up the contact surfaces before it loads it. So that's why I've positioned it like that. We can zoom back out now with that button. All right, so now what we want to do is go over to that part 4 in the instances. We're going to right click it in the feature tree and hit suppress. We're going to suppress that part, and we're going to go over to the mesh. And this is our old mesh that we had before. And what we want to do is actually check the mesh parts. Okay, so we're going to assign the element type and then select these 2 regions. And what we see there is you come up with the element library as standard, where it's 3D stress, and the geometric order is linear. That gives us a C3D4, a 4-noded linear tetrahedron that the simulation is going to be run with. And that's good because that's actually what Abacus explicit can take. And so when I talked a little bit about the restart file has to pass the same type of elements across, this is one of those cases where sometimes it might give you a quadratic by default, or sometimes the result's different. We want to make sure that the element types are consistent. So we'll go ahead and say OK to that. We didn't actually have to do anything here because we set it up last time, if you remember. All right, so the next step we need to do is actually ask for the restart file to be written out. So we'll go over to the step module and we'll select output restart requests. And here you can put a number of different things here. We're just going to go with 1, which will give it to at the very end of the step. So the frequency equals 1 and say OK. At this point, this simulation is ready to go. We're actually not going to, this whole planar part that we just ran with is actually suppressed. It's not going to be included in the simulation. And all we've done here is ask for a restart file to be written in the current problem. So we'll go back to our job module and making sure that I'm in app 8, and then we're going to go to the job manager and we will submit this job. Again, this is a quick one. It's just a static problem. Okay, and just like last time, that job finishes quickly. So we actually are not even going to look at the results. We do probably want to check that we have a .res file. So go back to this directory and do ls-ltr, and it's not so easy to read. Let me do that again. And we see that we have that file written out, .res restart. So we're good to go for our next phase. So now let's dismiss that, and we're going to collapse the model 1. We're actually going to copy it. So we're going to right click and do copy model. Take the default name, and now you want to make sure that you have this black underline underneath model 1 copy. You can expand that tree, and this is now the job that we're going to work on. The first thing we're going to do is change this step type. So we're going to go over to step, and when we click on the manager here, it says, well, you actually have a static, you have the initial and then you have the static general. If you select the static general, In the packet, I go through different options if you delete that. And then when you delete it, sometimes you get this error that the packet walks you through, basically dealing with contact interactions and replacing that. There's another option that I've discovered since making the packet, and that is the replace option. So if we select the static general case and then say replace, we can actually just change that to dynamic explicit right away, and then we get the typical pop-up step editor, and then we can put a 0.01 in here, 10 milliseconds, and say OK. So this actually is nice because it doesn't give that error that the deleting it gives, and it keeps on the interaction. So if you dismiss this and go to interaction module, you actually see that our interactions were created and they were actually propagated. In part, why this works out is because we did this with the static general case in the last application, which of course works in the dynamic explicit case too. So we saved ourselves some work here. Of course, there are different ways you can do this, a number of ways. You can remove it and add it, re-add it, it's fine. It does not matter too much, but this was certainly a little easier. So we'll say dismiss to that. And then what we're going to do here now is we are going to turn that suppressed part back on. So if we go into part 4, we'll right click on that and say resume. Okay, and what we're going to do is make our rigid part now. Okay, so it doesn't matter necessarily how you align this, but what you want to do is first create a reference point. So you select this RP button here and select any vertex, and you should get this little RP-1 next to it. And then you can go into constraints, create a constraint with this button. We'll go to rigid body and then say continue. In this case, you have a lot of different things that you can make rigid. For us, we're actually going to select the body, and then you have to select which body. So then you're going to edit the selection, select that planar surface, and say done. Now remember, with a rigid body, I said you have to attach a reference point to it. So we're going to, here is where you do that. We're going to select this arrow and select our reference point we just made, and then we're all good to go. That reference point is now tied to the planar body, or really another way to say that is the planar body is tied to the reference point. Our next option is to apply the boundary conditions. So we'll go into loads, and here what we're going to do is we're going to apply an initial velocity onto the bolt assembly. To do that, first we're going to create a set. Okay, so what we'll do is we will select this create display group, and we're going to go to part instances and remove from the viewport that planar instance, and then make sure that you have your screen aligned so you don't select the RP1 point when you do a box select. So what I'm going to do is go to Tools, Set, Manager. I will create a set, Geometry, say Continue, and then I'm just going to do a box select like that and say Done, and that comes in as Set 2. Dismiss that, and then in this third button down here is Create Predefined Field. So when we select that, what we can do is select in a mechanical category and a velocity and say continue. Select our regions for the field. What we'll do is we'll select our sets here and say set 2 that we just created. We can even highlight that in the viewport. Say continue, and then the velocity is going to be in the z direction, 300 millimeters or 0.3 meters per second. Say OK, and we get all these arrows drawn on that. The other thing we can do with the predefined field is use that restart file that we created to give the initial stress state. So we'll go back to the predefined field, and we're going to select, in this case, other. Notice that we're in the initial, before the simulation runs, before that step takes off, and we're going to select the initial state, Say continue. And it says select the instances to assign the initial state. So we'll box select our bolt assembly again, say done. And then here it asks for, okay, what's the import criteria? So we're going to give it that job name, job-1 that we ran before. Notice that if you use a different name, you have to put that job, whatever it is, okay, job.res. So we use the default, which is job1, so we should be good. Say okay. And then now we can turn back on our part, add to the viewport, and we're going to give this rigid body a boundary condition. So we'll select this displacement condition, and then we will go with the initial state, and we're going to do it in castre, which means it's fixed everywhere. We can get rid of this and just select the reference point directly. From the viewport, say done, and then we want this last one. All translational and rotational displacements are set to 0. And we see that highlighted up here. The last thing we need to do is assign the mesh. So we go to mesh. We already have a mesh for the bolt assembly. What we need to do is get one for the rigid body. Now I want to make an important point here is you notice we didn't put any properties down. We didn't put any properties because it's defined as discrete rigid in the very beginning, if you remember that. It doesn't have any material properties, although I think that it probably could have some density, but since it's discrete and rigid, I guess that we don't have to even do density. It's interesting. So I'll just go right ahead and mesh the part and take the defaults for the seeds because I don't really care about this. The only thing I do need is these elements to work for contact. So that's one thing that you have to be aware of if you do this for a different problem. In this case, I know that it works. So here is our sort of entire mesh discretization. All right, so now I'm going to go to the job. I'll give this a save, and I'm going to create a new job. And we're going to make sure that's not job 1. We want it to be something different. So in this case, we're going to have a new job name, which is job 2. Continue, say OK, and then I'm going to go into the job manager. And I think it's a good idea here to do a data check to make sure it picks up everything. So I have this because I was checking it earlier. So the check is running. And the check completed without any problems. So I'm going to go ahead and write the input. And to make sure it's written, I'm going to go over back to my ACI and confirm that there it is. Okay, so I'm going to create, since it's an explicit job, it can take some time, I'm going to submit the job on ACI B. So you can open up a new terminal, and this will be my ACI B window. So I'm going to do SSH -L RHK12 ACI-B.ACI.ICS.PSU.edu. My password. And once you get through two-factor authentication, in my case, I was already logged in previously, so it didn't ask me for it. But you want to navigate to that directory, classes ME461-App8. Okay, you can see my files there. Now, I need a PBS script, which I didn't post. So I can actually copy one from app7. So what I'm going to do is a cp ... abacus, or it's app7. App7 is a directory /abacus_app7. I'm going to copy that here. So what does this say? It says copy one directory back and then go into app7 directory and copy a script called abacus_app7.pbs space dot. The dot means to here. We can actually rename this if we do // abacus underscore app8.pbs if you want to rename it. You don't have to. Push enter. Okay, and now I do a ls minus ltr. There's that PBS script. Now remember, I can't open up anything visual here and look at this file from ACIB. I actually have to do that over in ACII. And of course, these computers, ACII and ACIB, share a file system, so I see that file over here too. I can open that with gedit to take a look at what it says. So I'm going to use 2 processors, 30 minutes. I see an error. I see this probably doesn't hurt it, but you want to remove this line, actually. That's old. I should remove that. So we're going to load abacus, and then I see an issue here with the job number. So we don't want to run job number 1 right. We want to run job number 2. So job-2 is our input file name. So other than that, I think this looks okay. So we'll go ahead and save that, close it, and then from ACIB, we're going to submit that job. So we're going to do Q sub dash capital A open, and then abacus underscore app8.pbs. We get a job number back, and then I can see what the status is. Let me expand this here. Close this down a little bit. QStat, see, it's QStat minus URHK12. Okay, and there I see the job is in the queue, waiting to start. Okay, so we'll wait for that to start and complete, and we'll come back and visualize the results. Okay, that job completed. Now, I don't think it actually finished because it was running up all the way until like 30 minutes, elapsed time's 32, and it didn't finish yet. So, you know, this might be a sign, I haven't looked at it yet, but it might be a sign that I need to extend my PBS wall time, say, to an hour and let it finish. But let's open up and take a look at it. So we'll go back to the abacus, and then we'll dismiss this and go to visualization tab, and then go ahead and open. Well, we need to be in the right directory, so we need to go back to app8, and then our job2.odb is there. So we can open that database and look at the deformed configuration. And when we go to the frame selector, we only have about 5 steps there, which is a bit curious. I was expecting it to be a lot further along. One thing I noticed is that abacus, the simulation seems to be okay. One thing I noticed is sometimes abacus will run slower on certain nodes for whatever reason. So you might have gotten 20 before, whereas I only got 5. So what I'll probably do is rerun this to see how it goes. But a couple things you notice here: at time equals 0, that deformed state from the application 7 is here. Okay, so that's really useful. We have a predefined stress field. If we were to plot sort of the load, if we pick a node to look at, so let's say create XY data, and we'll go at ODB field output, and we'll look at elements and nodes. We'll actually look at, let's look at element unique nodal. Let's see, probably look at the spatial acceleration, look at the magnitude, and edit the selection. We'll go somewhere down near the bottom and then plot that. So because we only have 5 time steps, we get this versus time. We get this strange loading. So this is at 1, so it picks up from the last time step and then it adds to it, is what it does here. And it should look a lot more dynamic. So we're probably under-resolved in plot steps. You know, what we showed in terms of dynamic response is the block is actually, the deformed configuration shows that we're getting a lot of bounce back here, right? So if we align this, okay, and you step through these viewports, you can see that the component is really like taken off, okay? And if I go into the deformed configuration, take a look at, not that one, the common options, you can see that I'm actually uniform, so that's real true displacement, okay? And you can see the large gap. So we really wouldn't want to model anything past this. So this is probably a fine amount of time. You know, I'm actually at 2.5 milliseconds. So maybe we want to go back and run this again with a smaller time step. And a couple other things what we'll do, go back here and we will go to the step manager. Let's see here. Step manager will adjust this. Instead of 10, we'll go, so that's 2.5 milliseconds. That's our max time. We know that it's going to be pretty far off by then. The other thing I'm going to do is I'm going to go into the field output and I'm going to modify this. Right now it's only given 20 intervals. I want to bump that up to say 50. So I've got 50 plot steps. Sometimes I usually go with 100. You know, maybe we want to do that. It's fine. Say OK. Dismiss. I'm going to write that job input again. I'm going to write the input. Okay, I'm going to go back to my ACIB window. Okay, and I will submit that job again. One thing I got to do here, that because it quit early, what you notice is you're going to have a ls-ltr. There's my INP file. You're actually going to get a .lck file. So that's a lock file that keeps you from overwriting your results. So I'm going to remove that, job2.lck. Now it will run. And the other thing I should probably do is update that script, PBS script, so it runs a little longer. So I'll edit the PBS script, and instead of 30 minutes, I'm just going to do 1 hour. And see how that goes. Save. Okay, and now I'll submit it. Okay, so then we'll come back in a little bit and see how that job went. Okay, that second job completed. Let's take a look at that. I don't see a .lck file, so that probably means it ran successfully. So I'll go back to the visualization tab and go ahead and open job 2 again. And Abacus crashed, so I'll load it back up. Not sure why that might have happened. Maybe it gave me a little error there because I removed the old ODB file, so maybe it was complaining about that. Let's try this again. Okay, so there's the deformed configuration. Let me go ahead and align it. Looks like we have the similar displacement bounce off that we had before. When we go into now the frame selector, you see now I have 100 plots. So I can see a lot more detail of the impact when the bolt hits the ground. You actually see a kind of flash there. There it goes. Some wave that goes through it basically really quickly. If we plot this now the same way we did before with the unique nodal, do accelerations, and then select a node somewhere down there. plot. And there we see kind of more what we expect. So the initial time, we have a really quick jump, a high jump, and even it would be pretty interesting to even have more plot steps. So we can see that we separate down here at really 0.0005. So we can make the probably cut the simulation off here, keep the 100 steps, and we'd have a nice, really smooth curve on the acceleration. I mean, so we're pretty much plotting under resolved at this point. So there are things that we might be missing in there. We'll actually talk about that in the next application. It's pretty interesting. So roughly around this time, around 0.2, I guess it would be 0.2 milliseconds, we have a peak occurring that you could look at. So the other thing you can do if you want to sort of visualize this, in the packet I have some options about, and I think I talked about this before, but you can go to feature edges, say apply, and then if you want to color and style, actually it was in the other, you go to translucency and you can apply this, so you can make sort of the part transparent. Just again, it's a little neat feature to know about in the visualization tools. So I think we're going to end it there. Hopefully this was a pretty cool app to you, and hopefully you can think about ways you might use this in the future. Rigid body, restart files, reference points, all really important components that we will continue to use in future applications also. All right, so I'll see you next time.